go through, I guess, a problem by problem review of recursion one, but I guess like in general, like are folks getting the hang of this idea of kind of solving smaller problems on an ongoing basis, like where the basic setup is to have the recursion function be a super small be a super small function that solves kind of one specific problem, and then running that over and over again, as opposed to kind of having this massive function that kind of plans everything out from the very start. Like, did I just say make sense?
Concept makes sense.
Okay. What was the hardest part from the workshop this morning?
Setting a counter that doesn't reset itself every time.
Setting a counter to then reset. Okay. Okay. Yeah, I guess like in the word recursion, you almost want to get away from setting a counter to start with.
Then I guess the hard part is coming up with another way to add something every time without a counter.
Sure. Anything else? Right. Right. So like I guess like traditionally like when we've done these problems, right? It's the use of counters, especially like basically as either a global variable or as kind of like a fake global variable, is actually very simple for us to understand. Like if I was to if I was to ask you to add up all the numbers for me in an array, you would do like counter equals 0, and then you would iterate through the array, and every number you encounter you would add it to the counter, right? And then you return the counter at the end. And that's like that pattern is very much of an iterative approach, right? It's like I start with this that exists outside of my iterations. I then go into my iterations. The iterators modify something, and then I finally, as the last step, I give back to you the thing that I've been modifying. Recursion is a bit different, right? The idea behind recursion is, hey, look, like I actually can just like rather than kind of store all these intermediate values, I can almost just kind of take them and just kind of process them as I go along. So what's an example of a problem that we can solve with iteration? Okay, so backtrack a bit. The reason why we don't like to use counters in most cases, especially with recursive problems, is because once again, with counters, they usually exist outside of the recursive function, right? If you think about the point of recursive functions, that everything is completely independent, right? They're all self-standing. There's no kind of global variable that governs all of them. And so when we use counters, it basically makes it more difficult for us to have recursive functions that don't depend on something outside the functions. And generally, in most cases, you want your function to not be dependent on anything outside of the functions unless the user gives it to you, right? So if you think about all the workshop problems that we've done so far up to this point, things like calculating like the prices for something after sales tax and delivery fee, right? It's like, well, we'll give you the price, right? And that's really the only thing you need. Everything else you kind of figure out on your own. If I'm trying to convert a temperature, like I'll give you the temperature in a number, I'll tell you if it's in Fahrenheit or Celsius, and you should be able to do the rest, right? So functions are designed to be kind of self-contained blocks of code, and using global variables really kind of takes away from that. What you also don't want, especially if you use a global variable, what that also does is once again it introduces this idea that like, well, if you have a global variable keeping track of things and someone runs your function 10 times, that global variable is going to keep track of all 10 answers, right? And sometimes you may want that, but most times you don't. So by having everything be contained within the function, as a user, you're also guaranteed that each time you call a function, you're starting with a blank slate, right? That you're starting with with a blank template, and now anything that runs at this point forward is going to be your code, as opposed to carryover or legacy code from previous runs of that function. So we're not going to get away from it. In fact, we're going to kind of go a little bit more into it in the second section, recursion two. And really, like I guess recursion two is once again, let me caveat this by saying that the problems that you'll see on the interviews and the assessment probably won't get to this level, but this is a natural extension of recursion. So as you go through it, like you don't need to feel super comfortable with it, but conceptually it should make sense. Um, Also in recursion two, we also start talking about like why someone would choose to do a problem recursively, and usually the most convincing answer, and usually in the real world, if you can do a problem iteratively, I think people usually opt for the iterative approach, right? They want the for loops, they want like the thing that's maybe a little bit easier to understand. But most people tend to resort to recursion when there's no other option, right? As in, I have a problem that only recursion can solve. So what's an example of something that recursion is really good at? Well, in case those 3 bullet points aren't a hint, um, the idea of nesting arrays and nesting objects was something that we talked about in both the arrays and the object section. Um, One thing that we did talk about with, for example, traversing nested arrays was we said, well, we can write a for loop, right, that goes through every single element. If it encounters, a number or a string, we'll do one thing, and if it encounters an array, we'll just iterate through it again. And that sounds good in practice, but we also talked about how arrays can be infinitely nested, right? Like there's no real cap to how many times you can nest something. And so if someone was to say, hey David, I have this array and I don't know what's in it other than the fact that it's either going to be arrays or numbers, um, it's kind of hard for me to pre-know exactly how many layers of nesting there's going to be. And more importantly, if someone decides to change it up last minute, I don't want that to break my function, right? So if I write like 8 for loops in there saying, all right, I can handle up to 8 levels of nesting, and someone's like, oh, by the way, there's one thing I changed to now, it's an extra level. Like I don't want that to just break my code, right? And so what recursion allows you to do is, because recursion, if you think about the concept, right, the point of recursion is we will do this problem until we reach an endpoint. Recursion is actually really, really great at handling problems where the endpoint is unknown, right? If to put it in the iteration standpoint, with an iterative function, we always say array.length or something.length, right? As in we know how many times we're probably going to run this thing. With recursion, it really shines when you say, I don't know how many times I'm going to have to do this, but I need to either run it I need to run it until it finishes. Um, so this is obviously a kind of crazy, but also equally valid, like completely valid JavaScript array, right? It has like 8 levels of nesting or whatever it is, or 9 levels of nesting, and it's really hard to traverse. But we are gonna, but if we have to do it, we could write nine for loops, but once again, it's a lot of work, and sometimes it's just not worth it anymore to kind of build it hand out. Instead, in this case, recursion is really great. So let's think about kind of how this problem will look if we only had an array of just things, right? No other arrays. It was an array of only, we'll say, numbers, right? So far, if there was no nesting of arrays, and I just asked you to log out for me and every number in the array, well, that's really literally as simple as writing a for loop, going through the array, and printing out every single element, right? And that's pretty straightforward. It's been pretty consistent with all the problems we've seen so far. Now, if I said there was if there was kind of an additional layer of nesting, what could we do? If you remember when we did the arrays 2 workshop, there was a problem that we basically in the middle we had a check, right, to see if, hey, if an element is an array, do this. Otherwise, if it's a number, do this instead. That's kind of rings some bells, sound a little bit familiar, right? And so that was kind of our first foray into this idea, like, okay, if we want to traverse something, at every single juncture, we're going to reach a decision point, right? Is this an array or not? If it's an array, we're going to handle it one way. If it's not an array, we're going to handle it another way. But if you think about it, if it's an array, like if the goal of this function is to print out every single number, if the element is a number, what do we want to do with it? Not a trick question. Sorry. In this function right now, assuming everything in an array is a number, based on what I've written so far, if I check every element and every element is a number, what do I want to do with it if it is a number? Right. I just want to print it out.
Yeah.
Right. However, if it's an array, what do I want to do with it? Let's be more specific. Not just iterated, but do what?
And then print each sub-element.
Right. So basically, if it's an array, I basically want to have my function be able to go through the array and print out every single number in it. And so, and if one of the things in that is an array, what do I want to do with that third level nested array? I want to go through that array, go through every element, and if it's a number, I want to print out with it. And notice how at every single juncture, no matter how many layers of nesting we're going into, I basically want to do the same exact thing over and over and over again, right? And that thing is kind of like the mini problem, right? Like the core problem we're trying to solve here. That thing essentially is at every single juncture. If someone gives me an array, what I want to do is I want to go through every element in the array, And then for every element, I reach a decision point. If it's a number, I print it out. If it's an array, I want to do to that array what I'm currently doing to my current array, if that makes sense, right? So if I had an array of 1 comma 2 comma 3, my goal is to go through and print out, go through every element. If it's a number, print it out. In this case, all 3 are numbers. I want to print them out. But if the fourth element is another array of 4 comma 5 comma 6, well then I want to do to that inner array of 4 comma 5 comma 6 the same thing I've wanted to do to my outer array of 1 comma 2 comma 3 comma array of 4 comma 5 comma 6. Yes? No? Okay. So once we start thinking about the problem that way, we kind of realize that, oh, like we actually only need one function, and really like the tricky part is not necessarily like what that function does, but rather how we want to call that function or when we want to use that function. So here, here is like, I guess like a somewhat like very simple but very kind of idyllic example of how that approach would look, right? I have an array called logs an array, and what does it do? It takes in an array, right? And notice how here like we're using a for loop, and you might think like, well, I thought we were doing recursion, but really like recursion and for loops are just tools, right? And so if within this body we want to use a for loop, like that's totally valid, right? There's nothing that precludes us from using it. What we don't want to do is it's like, and actually with this problem, it's going to be almost impossible for us to solve using only for loops, right? So with this problem, actually go crazy, use whatever you want, but pretty soon you'll come across that, hey, without recursion, I really can't solve this problem because no matter how many for loops you write, it might never be enough. Okay, so in this case, what I do is this function takes in an array and it goes through every single element in the array. And line 3, yep, we define the element. On lines, and then between lines 5 and 10, we basically have our fork in the road, right? Our fork says if the element is an array, we do one thing. Otherwise, do this other thing, right? You see that? If it's an array, we do lines 5 through 7. Otherwise, we do lines 8 through 10. So looking at this code, what's our base case?
It's an element.
It's always going to be an element. What's our base case here? Right. When do we call the recursive function? Right. So here, like at every juncture, what I'm saying is on line 5 says, okay, if the element is an array, we call another instance of this function, right? If you remember our countdown function, like this is the same idea, right? It's like if this condition is met, we iterate another version, we generate another version of this function. Otherwise, we just console log. And it actually doesn't really matter what's inside the else block, as long as it's not another call to the function. It means this is our base case. This is when we stop. Okay. So now, if we think about it that way, what this function is really saying is, hey, when you give me an array, I'm going to go through every single element in the array. Okay. If it's going to be a number, I'm going to print it out, and we're done with that element. We move on to the next element, right? However, if it's an array, I'm going to recursively call this function again, and it's going to handle it. And after it's done handling it, what do I do next? I move on to the next element, right? If it's another array, I will do this thing again. It will handle that array, and basically that's my process, right? I'm going to go through and handle every single element. You might be asking, well, what if one of those elements inside of it had another array? Well, for better or worse, that's that array's problem, right? Like that's the next iteration's problem to handle, because the next iteration is going to get an array and it's going to do the same exact thing that I'm doing, which is saying, all right, you gave me an array, cool. Let me go through every single element. If it's a number, I'm going to do it one way, and in fact, that way there's no more function calls. But if it's an array, well, let me just call another iteration of this logs and array function, and I'll pass in that element, that array element, into that function, and that function will take care of it. And notice how every single time I do that, what I'm doing is I'm getting one level deeper into the function, but there's no cap to how deep I can go, right? because every time I call this function, it's going to go through one level of the array for me. And the key part here is that it's only going to go through one level, right? Notice how in this logs and array function, I have how many for loops? I have one for loop. So the last part of this problem that hopefully becomes a little clear to you is this is not meant to say, all right, I'm going to get to the bottom of this element. Not at all. This function is saying, all right, I'll go one level deeper for you. If you want to go any deeper than that, call the next guy, right? Call another logs and array, and that function will go one level deeper for you. And then if you need more depth, that function will call another function for you. But every individual function is only responsible for going in one level deeper, right? Instead, we use the power of recursion to determine how many times we call this function, so how many levels of depth we go into. But every time we call this function itself is only going to go in one additional level of depth. Is that clear? Cool. So now, if I was to logs an array of 1, 2, or 1, array of 2, 3 here, when I start going through that inner, this should be an array. Sorry, I didn't have the bracket around it, but that's an array. Right? So as I go through that array, my first element is going to be what? It's going to be a 1, right? So when I go through that for loop, and I do, is the element an array? The answer is going to be no, it's not. So I wind up on my else clause on line 9. So it's like, okay, for element index 0, I'm in my else clause. All I got to do is console log out the element, and I'm done. I'm done since I'm done with this element, and I console log out 1. Then my for loop says, okay, great, you have 2 elements, right? Go to the next element. And the next element, what's the value of it going to be? Right, an array of 2, 3. And then, so I go through the for loop again, right? Lines 3 through 10 again. I go to line 5, it says, okay, is that element an array? The answer is yes. And so at that point, what I say is, okay, great. In an array of 2, 3, I'm going to create another instance of logs and array function, right? A brand new function that's separate from this one. And I'm going to say, here, take care of it, right? And I'm going to put into it the array of 2, 3, right? And notice how, once again, right, I've basically resolved one level of depth, right? I haven't gone into 2, 3. In fact, I don't even know what's inside that array. All I know is it is an array, and the next iteration of this logs and array function needs to figure out what's inside of it. I don't care. I just basically got rid of that one layer, right? I just got rid of the 1 comma level of the array, and the second array I'm going to let the next person take care of. So when we run, in the second iteration of logs and array, is going to look like that, right? It's going to be fed in an array of 2, 3. And so great, let's run through our sequence again, right? We'll iterate through this array. Let's go through the first element. What is it? It's a 2. So what do we do with it? Oh yeah, it is not an array. So what do we do with it? Yeah, we print it out on line 9, right? We console log out 2. And then the for loop says, okay, great, you resolved the first element successfully. Let's resolve the next element, which is a 3, right? By the way, the entire time I'm doing this, has this function finished yet down here? No, right? This function can't finish because this, when I fed it in 2, 3, it's still waiting for that to resolve, and that's what I'm working on right now. Remember, on my call stack, this is my priority. I need to resolve this before this can finish. So while I'm working on this is like still active, if you will, right? Like it's still, my computer is still keeping track of where we are there. And so, jumping back to this 2, 3 array, I go to the second element. It's a 3. It's also not an array. I console log it out, and now what? One at a time. Someone. Osiris?
You go back to the fixed iteration.
I go back to where?
To the fixed iteration to finish with the one who was keeping track.
Yeah. So basically, after I'm done with the 3, I run line 9. My for loop says, okay, great, you're now done with the array, right? There's no more elements to check, and that means that this iteration of logs and array function, it's done, right? There's no more code to run. This entire logs and array function is one for loop. Once I reach the end of the for loop, I'm finished, right? So only at that point do I say, okay, great, logs an array of 2 comma 3 is finished, and to this function here that was waiting for me, like all I gotta do is say, yeah, I'm done. Like I am gonna return undefined, but if you notice like that actually on line 6 there, we don't capture the value that we return because it doesn't really matter. So we can say, all right, I'm done. Here's undefined, and at this point, once that's finished, okay, once we log out the 2 and the 3, we then go back to where we left off here, and at this point, what's this function say? This function says, like, okay, great, the second element got resolved. All right, for loop, keep doing your thing. What's the next element? And what's the for loop going to say? Too long. Or, you've kind of reached the end of the road, right? You've taken care of the one, you've taken care of the second element, which is an array, and there's no more third element. So yeah, as far as this for loop is concerned, you're done, right? You finish your for loop. So, and once we're done with our for loop, which ends on line 11, we see line 12, which says, hey, this is the end of the function. This is the last thing the function wanted you to do, and that means we're also now finished with this function. And so we reach the end of our call stack. Any questions, sir? Okay, does that make sense, everyone? Okay. And so do you also see why we couldn't really do this problem with a for loop, with only for loops? Right? Because of the for loops, like at some point you don't know how deep to go, right? This will just say, hey, look, I'm gonna take care of one level of iteration for you. If there's another level, pass it on to the next function, right? What? Yeah, it's magic, right? Yeah, in some ways it's almost like an assembly line worker who literally says, I'm gonna put the wheels on the tire. I'm gonna put the tires on the car. And literally, that's all I'm gonna do. The next guy will take care of all your problems, right? Like I'm gonna do my one small bit. And if enough people are willing to do that, then eventually, you don't know how long, you don't know when you'll get the answer, but the bet is you're gonna get your answer eventually. Okay, so then this is literally just another example of the same type of problem. Here, the idea is we have an array of letters, and similarly as before. What we want to do is we want to take all of the letters in the arrays, no matter how nested it is, and join them up, right? And so here we're gonna see us use a counter, but the way that we use a counter here is it's different than the way we traditionally use counters. Traditionally, when we use a counter, that's kind of like our final answer, right? Like that's like the last thing that we want to return. In this case, the counter is not the final answer; it's just an intermediary tool that is going to be used every single run of this function, much like how we use the for loop in the last function. Okay, so how does this look? Well, if I had an array of just characters or just strings, this pattern should look very familiar, right? We have a final string, we iterate through the array, and then for every element, we pretty much just add it, we concat it to the final string, and then on line 7 there, when we're done, we return final string. Right? Very standard, very typical way of how we use counters. But if this array was heavily nested, how would it be different? Well, the most important thing to realize here is that once again, right? What's the mini problem we're solving, right? Like what's if you were this function, what's kind of like what do you want to be in the domain of things you do versus things you don't do? And the quick and simple answer is, well, just like in the last problem, I can't do too much, right? If you have a string that's like nested 9 levels deep, I can't go through all 9 for you. I'm just going to go through one level for you. And the next person will go through the next level for you. And the next function will go through the next level for you, right? So once again, we want to make sure that every single juncture, we want to kind of keep our function as contained as possible. And yes, we could write a function that goes in 2 levels deep every single time, right? So that way, let's say I have something that's nested 8 times, right? If we had a function that only goes 1 level deep, we would run it 8 times. If we have something that goes 2 levels deep with each function call, we run it 4 times, right? But really, with recursion, you also want to kind of boil your problem down to as simple as possible, and that's why you always want to default to kind of going 1 level deep. Okay, so here the idea is the same as before, right? In fact, if I gave you an array of just strings, this also handles the solution equally well, right? We have all the code we had before. The only difference from what we had before is line 5 there. Between lines 5 and 7 is we basically check to see if the element is an array, If it is an array, what do? Well, if the element is an array, we actually just say, hey, instead of adding that letter to the final string, let's add the recursive call to the final string. And so what does that really mean for us? If we take a step back and look at this concat else function, right? At every single iteration of this function, what we're saying is hey, look, you're gonna give me an array, and I'm just gonna give you all the letters from this array added together, concatenated together, from this point onwards, right? I don't know what you have when you called me, but I'm just gonna tell you what I have, right? So at each successive call, we're passing them a smaller and smaller array. And so if I was to look at this example here, right, like the array of A and then comma and an inner array of B comma C, when we are in the outer array here, the first time we do this, we're going to go ahead and A, it'll be like, okay, great, is A an array? No, it's not, so we'll just add it to final string. So now my final string has the letter A, right? And then when I reach this inner array, what I'm going to say is, is this element an array? Yes, it is. Great. Why don't you figure out what I get when I add up all the letters inside this inner array? Okay? And once you give back an answer, I'm just going to shove it onto my final answer. And so that's what this first iteration of this array is thinking. But in the second iteration, where so assuming this was this, well, that's going to call this function again, right? On just this B comma C array. What that array is thinking is, oh, great, you gave me an array of just B comma C. I don't know where you left off, but all I know is I'm going to do what? I'm going to go through this array and give you all the letters shoved together from this point forward. So how does that look? Well, initially we call this array of A comma B comma C, and our final string is just empty, right? When we iterate through the first letter, we get the A, and when we iterate through the second element, we get that. Well, in order to figure out what that is, we need to call concat else to just B comma C again, right? And now notice how concat B comma C is going to have its own counter. It's going to have its own version of counters of final string, and it's going to have to start empty, right? Because as far as this second iteration is concerned, as far as this is concerned, it doesn't know anything about this. It just knows, what am I, right? Like, the problem you asked of me is just to say for me to go one level deeper and give you everything that I have. And so it by definition should be starting off blank. It should be starting off with a fresh template. And so when that goes through it, it's going to add the B, it's going to add the C, and then it's going to do what? Right, it's going to return on line 11, right? The second this function here, it's going to say, great, my final string is B comma C, I'm done with the for loop, and now let me return this this final string value, which is B comma C. And by the way, who called it? Our first function called it, right? So once it returns BC, that outer part is done. That outer function is done. We now look to see where we left off. And where we left off was, well, we were waiting to figure out what was inside this inner array. And here it says, oh, it was BC. So now we can actually just add this BC to the A that we had before. And it basically serves as a de facto of, it basically is our way of traversing through everything. Notice how even though we are using a counter here, right, the counter is not a global counter, right? The counter is not going to have every single letter that we've seen probably it's not going to keep track of every single letter at all times, right? It's not going to, like that counter, this final string, it never crosses more than one iteration of the function at a time, right? Because every function is going to have its own version of final string. Every function is going to have its own counter. What it's really doing is it's saying, hey, I'm going to just do my micro piece, I'm going to do my work, and I'm going to hand it back to whoever asked me for it, and I'm going to wash my hands of this, and I'm completely done, right? And so it's up to the person who called it to now say, oh, okay, great, this is what I wanted. Now I'm going to add this to my work, right? If you ever, I guess, like in a professional workplace, let's say you had a project, right, and you had a team, right? Like your CEO might do one part of it, your manager might do the next part, and then you might do the last part, right? Once you finish your part, what do you do with it? You start from scratch, you do the work, but then you give it back to your manager, right? And it's up to your manager to figure out how this fits in with his or her work. Once they figure that out, they'll package it up together again, and they'll hand it back to the CEO to now kind of to package it up with his or her work there, right? So at every single step, even though we have a counter here, no function is ever modifying anything besides their own counter. Okay, so counters aren't bad. It's just you really need to understand and be comfortable with the scope in which that counter is being used. In this case, the scope of the counter does not extend beyond the function itself. So every function has its own counter, and that final value is never going to be used outside of that function, except when we return it. But when we return it, we're actually just doing what? In this case, we're actually just doing a copy of it too, right? So it's like this the final string variable itself never leaves this function. The value might, but the variable itself never leaves this function. Cool. Yes. Awesome. That's pretty much it. We have one more example for nested objects. This is so this basically is it's very similar to the two previous problems we've done, except rather than traversing through an array, we're traversing through an object. In this case, the problem is the point of the problem is every value in this object is either going to be a number or another object. I'm going to go through this a little bit quicker because there's not anything new conceptually here other than the fact that we replaced our for loop with a for in loop. Like that's the only difference, right? The for loop lets us iterate through the array. The for in loop let us iterate through the keys and the values of an object, right? So other than that, everything else is pretty standard. So just to walk through this code here, Okay, so here the point is we want to have a function that can go through that inner array, that really nested object down there, and add up all the values. And we know the values are either going to be objects with their own values, or it's going to be numbers, right? So how do we do this? Well, this looks identical to the string problem. We start on line 1. We keep a counter on line 2 of sum. We start at 0, and then we say, hey, for every key in the object, let's get the value there on line 5. On line 4, and then we're saying if the type of the value is an object, we're just going to add recursive call of whatever the sum of the inner nested object is to our sum. Otherwise, we assume it's a number, and we just add it directly to our sum. And at the end of the problem, we return our sum, right? So literally, this could be almost a copy paste of the previous example where we went through the string, except instead of having final string, we have a sum, and then here instead of checking to see whether or not something is an array, we check to see if something is an object, and then here, rather than iterating through an array, we're iterating through an object, but like everything else is almost identical. So let's just walk through it. We have that really nasty object there. As we iterate through every single key, the first key we encounter is going to be A, so the value for A is what? It's 1, so that's our sum so far after we go through the first one. When we get to B, we realize that the value for B is an object, so then we got to feed that object into another iteration or another call for sum vals, right? So, I'm sorry? Oh, yeah. So for sum vals, we do the same thing again. We start at sum equals 0. We say, great, what's your value? Oh, great, my value is an object. So we got to do this again, and then similar again. And then lastly, we get to this inner value here. We say, great, let's start for sum val for this inner object. What's the first value? The first value is a 2, so we have a 2. The next value is a 3, so we add a 3 to it. Now we have a 5. And then we finish our for loop, so we return that 5 to whoever called us. In this case, the previous one that called us was wanting to add it to their sum, which is 0. So now their total is 5, and then that's gonna finish and they're gonna return that 5 to whoever called them, and we just work our way backwards, and finally we get 1 plus 5 equals 6, and that's our final result. Right. So it's literally the same exact path that we saw in the previous problem, except now we're just using objects instead of arrays. And then I guess very similar to the previous array problem, right? Whereas in the previous problem, for every array, we were going through one level of depth. Here, for every object, we're going through how many levels of depth? How many levels of depth is each iteration of this function traversing through? Just one, right? All I'm doing is I'm using a for loop once. I go through the keys. If it's a number, I do this. If it's an object, I pass it onto the next function, right? I never look inside there. I never go through this object more than once. So just like the previous problem, we are also iterating through this object one level at a time, or each iteration of the function is iterating through it one level at a time. Cool. All right, that's it. Recursion 2. How y'all feeling? Okay. All right.